this video, we're going to look at the reaction and mechanism for the cyclopropanation of alkenes. The cyclopropanation reaction is a reaction in which an alkene reacts with a molecule called a carbene to form a product that has a cyclopropane, or a triangle, where the pi bond used to be. Here we show it with the CH2, and here we have it in skeletal structure just showing a triangle. This reaction is stereospecific, just like with epoxidation, where if you start with a trans alkene, you'll get a trans product, and if you start with a cis alkene, you get a cis product. As you see in this three-dimensional drawing of the same product, not forgetting that we have hydrogen atoms here also trans to each other. Wait, what's a carbene? Carbenes are something you've likely not seen before now. A carbene is a very interesting, unhappy, unstable molecule as follows. We have a carbon atom with two bonds. In this case, I'll show hydrogens, one lone pair, and that's it. If you count it up, you'll notice that we have a total of 6 electrons, not 8, in carbon's octet, leaving us with an empty p orbital. But despite the incomplete octet, this is still a neutral molecule, which we can prove using the formal charge shortcut that I have linked below. Carbon should have 4. Directly attached is 4 for a formal charge of 0. But wait, if you use the hybridization shortcut that I teach linked below, you'll see that having just 3 groups around the carbon gives us sp2 hybridization with an empty p orbital. All of these things come together to give us a molecule that is both a nucleophile and an electrophile. A nucleophile that wants to attack using its lone electron pair, and an electrophile that invites an attack into its empty p orbital. Sounds insane? Actually, yes. That's why it's so reactive, and that's why we need special circumstances when working on this reaction. You will likely learn 2 common cyclopropanation reactions. The first uses a haloform with a carbene intermediate. For this reaction, we start with an alkene, here we're showing trans-2-butene, and react it with a haloform such as chloroform, CHCl3, in the presence of a strong base like tert butoxide, to give us the carbene intermediate, for a final product that has our cyclopropane, but with 2 halogens attached. The second is the Simmons-Smith reaction, using a carbenoid rather than a carbene intermediate. This reaction begins with an alkene, in this case trans-2-butene, reacting with CH2I2 and a zinc-copper couple to give us the cyclopropane product. The intermediate, as we'll see when we look at the mechanism, is not quite a carbene because carbon will have a complete octet thanks to the help of the zinc-copper. So how does this work? Let's jump into the reactions. Because the carbene is so unstable, we don't react the alkene with a carbene. Instead, we create the carbene right as we're doing the reaction. In this case, we start with chloroform and bring in a strong base like tert butoxide. Tert butoxide uses one of its lone electron pairs to grab a hydrogen atom off of the chloroform and collapse those electrons back onto carbon. This gives us a very unhappy carbon and a tert butanol on the side. Even though it has a complete octet, it has a negative charge. The negative charge is stabilized by the highly electronegative halogens, in this case chlorine, via the inductive effect. So much so that one of the chlorines ultimately gets so excited to the point where it completely takes away the bonding electrons and breaks away from the molecule. This gives us a Cl-, just floating around somewhere in solution, now that it has that extra lone pair that it stole from carbon, as well as a neutral molecule that has a carbon atom, the 2 lone electrons from the initial hydrogen, and the 2 remaining halogens. This is called a dihalocarbene, in that we have 2 halogens, in this case 2 chlorines, sitting on the carbene with only 6 electrons in its valence, made by having 2 bonds and 1 lone pair. This reaction, using a strong base to grab a hydrogen off a carbon and ultimately kick out one of the halogens, should remind you of another elimination reaction that you've seen, except for one major difference. This is called an alpha elimination reaction because both hydrogen and the halogen come off of the same carbon atom, in contrast to the beta elimination that you've seen for the E1 and E2 reactions, where hydrogen and halogen come off of neighboring, one off the alpha and one off the beta carbons. Now that we have a carbene, let's take a look at the alkene. For the sake of this reaction, let's take a look at cis-2-butene reacting with dichlorocarbene. Remember that the carbene has an empty p orbital which likes to get attacked and has the lone electron pair that likes to do the attack. And so the reaction happens as follows. The alkene has a nucleophilic pi bond, meaning the pi electrons want to attack, and attack they will right into the empty p orbital of the carbene. At the very same time, the carbene will use its lone electrons, which are also nucleophilic, to attack the other carbon of that pi bond. This is not a step 1, step 2 reaction. This is a concerted mechanism where both nucleophilic electron pairs, the pi bond and the carbene, are going to attack each other at the very same time. What do we get? The carbon skeleton retains its stereochemistry. That means the two methyl groups are still cis to each other. We have a bond between this carbon and the carbene carbon, where the pi bond attacked, and another bond that we showed in purple electrons where the carbene attacked our molecule right back. And of course, let's not forget our two halogens sitting on top of the cyclopropane. If you're asked to show the stereochemistry, consider drawing these two methyl groups either both on dashes or both on wedges to show that they are still cis to each other because we started with a cis alkene. The Simmons-Smith reaction is slightly different because we're not reacting with a carbene, we're using a carbenoid. A carbenoid is very similar to a carbene, but it's lacking some of those properties, namely an empty p orbital because of an incomplete octet. But let's back it up. For this reaction, we're going to start with CH2I2 as the source of carbon and react it with the zinc-copper couple. The zinc is going to insert itself between the carbon and the iodine to give us a molecule that looks like this. This right here would be our carbene, except instead of a lone pair, it has the halogen attached. Instead of an empty p orbital, we have that zinc iodine also attached. Why is this so important? Compared to a carbene, this carbenoid is actually very stable. The mechanism for the Simmons-Smith reaction is very similar to what we've already seen, in that we have a concerted attack with one extra step. When the pi bond reaches out to attack the carbon, iodine gets knocked loose in the process. And in order for carbon to attack the pi bond, it has to let go of the zinc iodine. The way to think of this is imagine you're sitting at a ball game. You're relaxing, enjoying the game, eating ice cream. Suddenly, the ball comes right at you. Without thinking, what is your reflex reaction? You lift your hand to your face. You want to protect yourself. What happens to your ice cream? Well, let's just say you're not going to finish it, are you? When carbon gets attacked, it has to let go of its ice cream. Let's take a look at what happened to every piece in this reaction. Our skeleton remains the same. That means a cis alkene still looks cis. But now we have a red bond to the blue carbon where the pi bond attacked, and a purple bond where the carbenoid attacked back. We still have two hydrogen atoms because those bonds are hardest to break, so they haven't gone anywhere. And somewhere in solution, we have that ZnI as a side product from everything that we let go. If you're asked to show the stereochemistry, given that we started with a cis alkene, you can draw both of the methyl groups on dashes or wedges to show that they're still cis to each other. For even more on alkene reactions, including my entire video series, Alkene Practice Quiz and Cheat Sheet, visit my website linked below or go to leahversai.com/alkene-reactions. The link again, leahversai.com/alkene-reactions.